We've now seen a number of techniques for finding derivatives of various types and combinations of functions. Now, we're going to turn our attention to how to use those derivatives to solve various problems and model real-world scenarios. And where better to start than to explain why graphs have the shapes they do? Every so often, I think it's worth it to just take a step back for a minute and look at how far we've come. It helps to bring everything together. At this point, we've developed formulas for the derivatives of a number of simple functions, some of them in videos, others through activities that we've done in class, as well as rules for how to deal with various combinations of these functions. And actually, I want to congratulate you for making it to this point. It can admittedly be kind of a slog when you first get into these differentiation rules. Before we go any further, though, let's talk for a moment about a hotly debated topic in education: memorization. Is it worth it to memorize these formulas for derivatives when you just look them up on Google? I've gone back and forth on this personally, and what I've settled on is yes, but a qualified yes. Here's how I see it. See, we developed all these derivative rules for a reason. We need them to be able to apply calculus to real-world scenarios. That requires more than just knowing how to calculate derivatives. You also need critical thinking, which means understanding what derivatives mean conceptually and knowing how and when to use them. But there are still cognitive benefits to being able to recall information from memory, what researchers like to call fact fluency. It frees you up to be able to handle those higher level tasks because you're not spending as much time and effort trying to rederive or look up all the basics every single time. And there's been loads of studies on what's called retrieval practice. Basically, the best way to recall information is to put yourself in situations where you have to recall the information. That could mean making some flashcards for your basic derivatives, or practicing problems where you have to use those basics. In other words, use it or lose it. If you do forget something, there's no shame in looking it up, or even better, rederiving it from other things you know. But try to use that to make it stick the next time. Now, all of that being said, memorization can't be the entirety of how you approach calculus, or really any subject, especially mathematics. Remembering basic facts can smooth out some bumps in the problem-solving process, but it's even more important to understand the meanings behind those facts, to see how they relate to each other and to your prior knowledge in math, and to be able to apply them in potentially unfamiliar situations. Calculus doesn't exist in a vacuum. Neither should your understanding of it. Open up just about any news site, scientific paper, or business report, and it won't be long before you find a graph of some sort. Like I said before, one of the best ways to understand a relationship is to visualize it. What calculus lets us do is describe the shapes of various graphs by appealing to their derivatives. Remember that the derivative in essence tells us the slope of a curve. In particular, it's useful to know about the sign of the derivative, whether it's positive or negative. Say we want to know about the graph of a function f. If its derivative, f prime, is positive on some interval, then that means the graph of f has a positive slope. It's increasing, going uphill as we go from left to right. Put another way, if x increases, then f of x also increases. On the other hand, if f prime is negative, then f is decreasing, going downhill. As x increases, f of x decreases. Let's see how this works by analyzing a relatively simple function. Say f of x equals x cubed minus 3x squared plus 1. What might its graph look like? To be fair, we could go to Desmos and check it immediately, but that would be spoiling the fun. Let's see what we can figure out on our own first. Our derivative, f prime of x, is 3x squared minus 6x. Notice that both terms have a common factor of 3x, so if we pull that out, we get 3x times x minus 2. If either of those factors is 0, then the derivative is 0 overall. So that tells us the graph of f will level off at x equals 0 and again at x equals 2. We'll put that information on a sign chart for f prime. Anywhere that the derivative is 0 or undefined is called a critical value of f, because that's where all the most interesting stuff happens. Those critical values split up the number line into pieces, and now we just need to figure out what happens on each of those pieces. Suppose we want to see what happens to the right of x equals 2. One thing we could do is test out a value like, say, x equals 5. Then 3x would be 15, and x minus 2 would be 3, so we'd have 15 times 3 equals 45. That tells us that f has a slope of 45 at x equals 5. But we can actually say more than that. If we pick any number bigger than 2, then 3x will be positive, and x minus 2 will also be positive. A positive number times a positive number is always a positive number, so no matter what, for all values bigger than 2, we can conclude that f prime, the slope of f, must be positive, so f must be increasing. We don't even actually need to do any arithmetic here. We can just reason things out based on the signs of the numbers, positive or negative. Let's do that with the other intervals while we're at it. What if x is between 0 and 2? Well, 3x will still be positive, but now since x is less than 2, x minus 2 will be negative. Positive times negative is negative, so between 0 and 2, f prime is negative. That means f is decreasing on that interval. Finally, what if x is less than 0? In that case, both 3x and x minus 2 will be negative. Now, negative times negative is positive. So to the left of x equals 0, we know f prime is positive. That means f is increasing. So to put it all together, starting from the left, f is increasing, then it levels off at x equals 0. Then it decreases until it levels off again at x equals 2. Finally, it increases for the rest of the graph. If we plug in some values to get a few reference points, we find that the graph should look something like this. Wait a minute, that doesn't seem right. This is supposed to be a cubic curve. Shouldn't it be, curvy? There's definitely something missing here. Well, it turns out there's more to figuring out the shape of a graph than just whether it's increasing or decreasing. We also have to pay attention to the curvature, and that means looking at how the slope is changing. In other words, we need the derivative of the derivative, which we call the second derivative. For example, say f of x equals x cubed, whose derivative f prime of x is 3x squared. Then the second derivative, which we write as f double prime of x, is the derivative of 3x squared, which is 6x. As you can imagine, we can keep going, taking a third derivative, a fourth derivative, and so on. Notice, by the way, that once we get to the fourth derivative, we kind of get sick of writing all those little prime symbols, so we just write which derivative we're taking in parentheses up top. Anyway, what does the second derivative tell us about the shape of a graph? Well, if f double prime is positive, then the slope of f is gradually increasing, which means it'll make sort of a smile shape. We say that the graph of f is concave up. Likewise, if f double prime is negative, then the slope of f is gradually decreasing, which means it'll make sort of a frown shape. In that case, we say that the graph of f is concave down. Okay, let's go back to our original curve we've been analyzing. Since the first derivative is 3x squared minus 6x, if we take the derivative of that, we'll get f double prime of x equals 6x minus 6. If we factor out the 6, that's the same as 6 times the quantity x minus 1. That means that f double prime of 1 comes out to 0. So we'll call 1 a second critical value of f. Then, by similar reasoning to what we did before, f double prime is negative when x is less than 1, and positive when x is greater than 1. So to sum things up, as we move left to right, f starts off concave down until x equals 1, and then switches to concave up. By the way, that point at which f switches concavity is often called a point of inflection. So if we combine that information about concavity with what we already know about f increasing or decreasing, then we have a much better picture, a much more thorough idea of what the graph should look like. And if we sketch it out, we find that it looks more like this. Now that's more like it. That's what we expect a cubic function to look like. The second derivative gave us the extra information we needed about the graph's curvature. You now have some new language to describe the shape of a function curve: increasing, decreasing, concave up, concave down. And all of that comes from analyzing the first and second derivatives of a function. The best way to internalize that language is to put it to use. So I would suggest thinking about all the different kinds of functions you learned about in your algebra and pre-calculus classes: powers, roots, exponential and log functions, trig functions, and so on. See how the terms we've used here apply to those functions. But you may even want to look for these kind of shapes in your everyday life as well. See if you can spot a curve that's both increasing and concave down, for example. Some rolling hills, a decoration in your house, a company logo. It can be anywhere. Calculus really is everywhere, if you know where to look.